All right, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Lise Turner, who's at the University of Waterloo, who's going to be talking about local analogs of Hadwiger's conjecture. Go ahead, Lise.
So hi, thanks for having me. This is joint work with Benjamin Moore and Luke Postal. The paper is up on arXiv if you want to see more details about this. So for today, we're going to do first a little introduction, history of Hadwiger's conjecture, which is almost certainly old hat for all of you, but you know, a little overview of distributed algorithms, and then what we mean by local properties. Then we're going to quickly go over Postal's work on graphs on surfaces, particularly the plane, and then use that as a jumping off point to talk about KT minor free graphs and local algorithms. Okay, so some standard definitions. A coloring is a function from the vertex set to a set of colors. A list assignment is a function that gives each vertex a list of colors. And a list coloring is a coloring that gives colors from within the list of every vertex. A graph is said to be k-colorable if it has a coloring where every vertex's list is the colors 1 to k, and a graph G is k-list colorable if for any list assignment such that every list has at least k colors, G has an L coloring. Okay, so the history of graph coloring goes back to the 19th century and the four-color theorem, then conjecture, for a long time. And he was wondering actually for regions of a plane, but with planar duality, this is exactly the question of can you four-color a planar graph? So this was proved finally in 1976 by Appel and Haken. And then Robertson, Sanders, Seymour, and Thomas gave a simpler proof in 1997. Still computer assisted, but slightly less long. Now, planar graphs end up being very closely linked with minors because of two major theorems. One is by Kuratowski, which says that a graph is planar if and only if it has no K5 or K33 minor. And then Wagner's theorem says that you can build any K5 minor free graph by clique summing on small cliques, planar graphs, and the graph V8. And so this brought Hadwiger to conjecture in 1943 that if G has no KT minor, then G is T minus 1 colorable. And so far this is known for T up to 6, and it's still open for T greater than or equal to 7. For large T, some bounds are known. In 1984, Kostochka and Thomason independently proved that KT minor free graphs are big O of T square root log T degenerate, and that gives a bound on the coloring. And for a long time, this was the best known result. And in fact, some people were starting to wonder if Hadwiger's might be false and this might be the best bound you could get. But then in 2019, Noren, Postal, and Song showed that KT minor free graphs are big O of T log T to the beta colorable for any beta greater than a quarter. And in 2020, Postal improved it down to big O of T log T to the 6. And then finally in August 2021, Delcourt and Postal improved this down to big O of T log T. And they also proved that if you can show a certain statement about small graphs, then you can actually get big O of T. So the next question is, what can we say about list coloring KT minor free graphs? Directly replacing coloring with list coloring in Hadwiger's conjecture gives you a false statement. Jaret and Wood showed that in fact it gives you a fairly false statement because there are graphs without a K, 3K plus 2 minor, which are not 4K colorable. Kawarabayashi and Mohar, in response to that, conjectured that all KT minor free graphs are 3T over 2 colorable. But that's also false because in October of 2021, Steiner showed that the constant has to be at least 2 minus little o of 1. So anyway, list Hadwiger is still open, but the constant is at least 2 if there is such a thing. For upper bounds, the degeneracy bound applies. The 2019 result was extended by Noren and Postal to list coloring, and Postal's big O of t log t to the 6 result also works for list colorability. Okay, so now let's switch gears and talk about distributed algorithms. So in kind of a classical graph algorithm, you have a giant computer, you feed it the entire picture of the graph, and it spits out your coloring or whatever it is you want. In the case of the local model of distributed algorithms, every vertex has a processor, and processing on that processor is free. And your kind of time factor is communication. So every round, each vertex can send messages of unlimited size to each of its neighbors. And then the complexity is just the number of rounds of communication that are required. So this models essentially collaborative problem solving on a network with high latency, which thankfully this is not one today, so that's nice. So now we need a notion of efficiency for these algorithms, because for kind of classical setting, we'd be talking about an efficient algorithm being polynomial time. But that falls down here because in polynomial time, you can do an entire graph traversal, breadth first, depth first, doesn't matter, get a complete picture of the graph. And then any one of your vertices can use its free processing power and just brute force the problem. So that's not what we want. So we're going to consider an algorithm to be efficient if it runs in polylogarithmic time in the size of the graph. Efficient coloring algorithms are known for some graph classes. So for graphs with maximum degree delta, the greedy bound can be found in big O of delta log delta plus log star of v of g. Log star here is the function that takes a number and determines how many times you have to apply the logarithm to it to make it smaller than 1. So it's sort of morally the inverse of the tower function. So it's very, very small. Graphs with bounded arboricity, there's also an efficient algorithm that finds a CA coloring in big O of A log V of G rounds for any fixed C greater than 2. Obviously, the smaller your C, the worse the constant hidden by the big O. So now let's pull those together and talk about what we mean by local in the title of the talk. So in a distributed algorithm, after R rounds, a vertex only has information about its R neighborhood. So if an R round distributed algorithm exists for graphs with some property, then it can also be applied to graphs that don't necessarily have the property, but where you can't certify this in R rounds. Because if you had an algorithm, an R round distributed algorithm that failed on graphs that don't have the property, you've just found a way to certify in R rounds that the graph doesn't have this property. So an efficient distributed coloring algorithm for graphs with some property, like no KT minor, planarity, whatever, implies a coloring result for graphs which locally have that property. So then the obvious question is, can we bound the chromatic number of locally KT minor free graphs? So kind of taking first of all, we've got a lower bound. It's not particularly strong, but it does exist. So there exists a graph G with n vertices, which are not t-1 colorable, but such that every neighborhood of G of radius less than linear has no KT minor. So for t equals 3, that's just a very long odd cycle. And then the generalized construction, it's a large number of copies of KT minus E. You glue successive copies on the endpoints of the edge you removed. It's sort of a cycle, and then you have a clasp edge. So it's basically like a necklace. And essentially, when you have KT minus E, if you want to color that with T-1 colors, the endpoints of the edge you removed have to be the same color. And that propagates all around. And then you've got your clasp edge that says, oh no, wait, they can't be the same color. All of a sudden you need T colors. So this is the construction. So in terms of upper bounds for t equals 1 and t equals 2, that's trivial because the property of having no edges or no vertices is a local property. Locally acyclic graphs are 3 colorable. There are algorithms from the 80s that 3 color acyclic graphs in big O of log star n time. So very, very efficient for locally acyclic graphs. And then sort of paralleling the history of coloring results, we look into planar graphs. So locally, planar graphs are 5 list colorable. The first result really on that was in 1988 by Goldberg, Plotkin, and Shannon, which gave a log V round algorithm, but required 7 colors. In 2018, Albuquerque, Bonamy, Bousquet, and Esperet improved that to 6 colors at the cost of cubing the runtime. And then Postal in 2019 gave a log V time algorithm that requires 5 colors. And this is list coloring, so that 5 colors is the optimal bound. So now for KT minor free graphs, in joint work with Ben and Luke, we've proved the following. So for t equals 4 or 5, there is a distributed algorithm that, given a KT minor free graph G and a T list assignment, finds the coloring in log V, big O of log V rounds. And for large T, if h of t is a function such that all KT minor free graphs are HT list colorable, oh, I missed the constant of 13, whatever. Then there is a distributed algorithm that, given a KT minor free graph and a 13 times the maximum of h of t and 31 halves T-1 list assignment, finds the coloring in big O of log V of G rounds. So this here, current best known h of t is big O of t log t to the 6. But hopefully that will be improved in the future. Postal and Delcourt conjectured that their methods for the coloring might give an h of t that's big O of t log t squared. So, you know, there is a hard lower bound on the constant if for this, if linear list Hadwiger does end up being true of 13 times 31 over 2. But apart from that, this result will scale as results improve for list Hadwigers. Okay, so Our algorithm is actually just Postal's algorithm with a couple of tweaks. So we'll first go over that real quick. So we need a couple definitions. So if C is a constant, a C pocket of G is a set P of at most C vertices which have degree at most C. And this is this degree is the degree in the graph, not just the degree in the pocket, because otherwise it would be completely trivial. A pocket P is D deep if the size of P is at most D times that of its coboundary. And a pocket P is C deletable if for any list assignment L of P, which has C colors, except on the boundary vertices where it has C minus the number of outgoing edges, G of P is L colorable. So we're going to be talking a bit about boundaries and co-boundaries. So if C is our pocket, oh yeah, I can control my mouse. If C is our pocket, its boundary, and G minus C is the rest of the graph, its boundary is the set of vertices in C that have neighbors in G minus C. And the co-boundary of C is the boundary of G minus C. It's the set of vertices that are not in C but have neighbors in C. So the general idea of Postal's algorithm is locally find a bunch of deletable pockets. And this is entirely feasible because pockets have bounded size, they have bounded degree, and the deletability condition is entirely internal. It doesn't depend on anything that's going on outside the pocket. Delete the pockets, recurse on what's left, and then extend the coloring back to the pockets. And again, we can do that no matter what happens in the rest of the graph because of we use a very, very strong notion of deletability for pockets. So here's the full algorithm. In Postal's version for graphs on surfaces and graphs in the plane, more specifically, he has an extra condition that when the graph is very small, he just brute forces it. We don't end up using that, but it's an option. So you really, the really clever part, which if you don't do it, you end up with an extra runtime cost of a factor of log star V, is once you've got all your pockets, you divide them into groups by essentially coloring a graph made up of your pockets so that they're not touching, and then you just color them back in batches. So you're recursing on something that's much smaller. Okay, so the idea of recursing on something that's much smaller requires another definition, which is of a specific set of pockets. So we're going to call this set of pockets a wallet. So if G is a graph and you're given constants C and D, a CD wallet is a collection of disjoint induced subgraphs of G such that all of them are pockets. All of them are either purses. So these are planar graphs with coboundary 2, such that if you add the edge between the two coboundary vertices, you still get a planar graph. The pockets are non-touching, so no common edges, no common vertices, and there's a lot of these pockets, so a linear number in the size of the graph. So it now suffices to show that these wallets exist and that they're deletable. So purses are deletable. This is by a result by Thomason on short pre-colored paths in planar graphs. Deep pockets may not be deletable themselves, but they contain deletable subpockets. And because our notion of wallets being big is based on the number of pockets, not the size of the pockets, we can pass to subpockets without breaking our wallet. And so this comes from the theory of strongly hyperbolic graph families. So now, in terms of getting a lot of pockets, Postal combines results by Lipton and Tarjan and a result by Mader to prove that there is a small separator that breaks your graph into a whole bunch of pockets. So now you have a lot of pockets. The question is, how many are going to be eligible to be put in a wallet? So bad pockets are pockets that are not purses and that are shallow. They're not deep. So you want to contract all the shallow pockets that have coboundary at least 3. And that gives you still a planar graph. So you can bound the number of edges in this graph using the size of X, your separator, and Euler's formula. And that gives you a linear bound. For non-purse shallow pockets of coboundary 2, they have to form a force on X. And this is because if there was a path joining the 2 coboundary vertices elsewhere in the graph, then you can contract that down and it would break planarity because you assumed it's not a purse. So you can't have those. And of course, forests have bounded size, again, a linear bound. So you also have that shallow pockets themselves have a bounded size and the size of their coboundary. Put that all together, you have very few vertices that are in pockets that have to be thrown out. And so you have very few pockets that have to be thrown out. Okay, so that's Postal's algorithm for planar graphs. And now let's move on to how we tweaked it and adapted it to KT minor free graphs. So what we need to show here is that deep pockets contain deletable subgraphs. Certain classes of pockets with small coboundary are deletable. So this is because the notion of purses is very tied to planarity, and planarity is no longer really relevant here. And also that we can bound the number of vertices in bad pockets. So in terms of deep pockets, let t equals 4 or 5. There are constants CT such that if G is a KT minor free graph and has no T deletable subgraph disjoint from X, V of G is at most CT times the size of X. And here for X, we're going to be using the size of the coboundary of the pocket we're looking at. So essentially this tells us that deep pockets contain deletable subgraphs. Now, the constant for t equals 4 is something like 11 or 12. The constant for t equals 5 is really terrible. It's something like 43 times the constant that Postal gets, which is also pretty large. So it's an, this is not the kind of algorithm you want to be running if you have any other choice. This is really just for big graphs. And then for general t, and I've forgotten the constant of 13 again, there are constants C of t such that if G is a KT minor free graph and has no 13 times the maximum of H of t and 31 over half t minus 1, deletable subgraphs disjoint from X, then V of G is less than or equal to CT of X. And in fact, the lemma is a little bit more involved than that because to make the induction really work for general t, instead of using a constant times the size of the graph, size of the separator, you end up using something interesting where you sum over the small degrees of the vertices and then multiply the cutoff degree times the number of vertices of large degree. So it gets a bit more involved here, but morally it's the same. Okay, so the complete proof for t equals 4 is, first of all, you note that K4 minor free graphs are exactly those with tree width 2. So you have a graph, you take a too smooth tree decomposition. So too smooth here means that every bag has 3 vertices and the intersections of the bags have exactly 2. Low degree vertices have to be in X because they're deletable themselves. So leaf bags have to contain a vertex in X. high degree bags have corresponding leaf bags just because of how degrees work in a tree. And so you're just left with the conundrum of what do you do with long paths of degree 2 bags. And then you just kind of go through it and you realize that either there's a vertex sticking out that's just in one bag, so it's low degree, so it's an X, or it contains a copy of this little deletable gadget. So here, these are the co-boundary. So these are the outside vertices, and then you can color this with lists of size 2, 3, 3, 2. So for t equals 5, it gets a little bit more involved. It's still the idea of building a tree structure. So you're building a tree using Wagner's theorem, but you're building a specific kind of tree. No degree 2 planar bag has a planar neighbor, and adjacent planar bags intersect on exactly 3 vertices. The first one, you can either merge the bags, or if you can't, you can kind of split one of the bags and end up with a degree 3 bag. And then for adjacent planar bags intersecting on exactly 3 vertices, if they just intersect on an edge or a point, you can just merge them and it's going to be still planar. For the planar bags, you just use Postal's result from hyperbolic families straight out of the box. Low degree V8 bags have low degree vertices because V8 is itself 3 regular. So if they're not hanging on to a whole bunch of other bags, they have low degree. So then you use the same ideas of pairing high degree bags and leaf bags, and you're done modulus and computation. So we've dealt with our deep pockets. So let's deal with our purse analogs, or pockets of small coboundary. So pockets of coboundary 1 for t equals 4 are 4 deletable, even when you double count that vertex. And the proof is you proceed by induction, and you use the fact that if you have a coboundary vertex and a cycle that doesn't contain it, you have to have a 2 separation between the 2. Because if there's 3 disjoint paths from a vertex and a cycle that doesn't contain it, that's right away a K4 minor, which you can't have. So, so what you do is you take both sides of this 2 separation, contract 1, double counting the contracted vertex, extend the coloring, and then contract the other side, double counting the contracted vertex, color this side by induction, and then you split it up and voila, you're done. And this is really nice, gives you something similar to purses, and it deals with your pockets of coboundary 1 and your pockets of coboundary 2, where you can add an edge without breaking K4 minor freeness all in one go. You don't have to handle them separately. For t equals 5, because there's been so much work on K5 minor free graphs and planar graphs and whatever, there's this beautiful result by Skrzykowski from 1998 that directly gives you that if a pocket has coboundary of size at most 3, and that coboundary could be made a clique without creating a K5 minor, then the pocket is deletable. So for dealing with pockets of coboundary 3 when t equals 5, where they can't be made a triangle without creating a K5. So what you want to do is you want to contract those pockets, delete everything other than them and their coboundaries. And the resulting graph has to have a cut of size 2 between any contracted vertex and a cycle that doesn't contain it. And the reason here is that suppose you have your contracted vertex. So this represents 3 vertices and a pocket behind them, such that if you put a triangle around these 3 vertices, you would get a K5 minor. If it has 3 disjoint paths to a cycle, you can just contract the cycle back up on top of it. and you end up with that triangle that you couldn't have. So you have these cuts of size 2. The contracted vertices form an independent set. And then with some induction, you can show that graphs with these specifications have at most 2v minus 4 edges. And here, the really crucial thing is, as long as you're density bound, the coefficient of v is smaller than the co-boundary that you're working with, you are done, because you can get a linear bound on the number of pockets in this situation. So then you bound the number of vertices in these pockets, because if we're considering them separately, they're shallow. Okay, so for pockets of big co-boundary, K4 minor free graphs have at most 2v minus 3 edges. So any shallow pocket of co-boundary at least 3, we can just bound those linearly in one go. And bipartite K5 minor free graphs have at most 3v minus 9 edges. So pockets of co-boundary at least 4 that are shallow, you create a bipartite graph by only keeping, by essentially removing all the edges within X and only keeping the contracted vertices and their neighbors. So then any shallow pockets of co-boundary at least 4, you can bound all the vertices in there. So yeah, so you've got a bound on the total number of vertices in these bad pockets. You subtract everything, you're left with enough pockets to form a wallet. And it's the same idea with bad pockets of co-boundary 2 that can't have an edge added, they form a forest. For t equals 5, bad pockets of co-boundary 3 are a complete and utter pain, but they can be handled. You just end up like running up the thing until you reach a contradiction. So then that concludes the proof, and you can use Postal's algorithm as is. And in fact, it's a little bit simpler because you can just recurse until you're done. You never get to the point of having to brute force a graph because it's gotten too small to be able to recurse on. So some comments on the large T proof. The proof for large T uses induction on a single cut rather than a tree structure. And the result here you use, so it's kind of a 2-stage process. First of all, you assume a minimum counterexample. And first of all, you show that all its vertices have to have high degree. And then you show that, and then there's this nice result that gives you that if a graph has high degree and high connectivity, then it has a KT minor. And so you say, okay, well, we've already shown that it's got high degree, so it can't have high connectivity. So you get a small cut. And so you use induction on the small cut. And then you break into cases, you use some bipartite density results, and it all works out in the end. Yeah. So thank you very much for coming. Does anyone have any questions?
Thank you so much, Lise. Let's do a round of applause first, and then we'll go to questions. So if everyone can please unmute, and then I'll count to 3, and then we'll clap. 1, 2, 3. Excellent. Thanks, everyone. All right. Does anyone have any questions? The algorithms seem really cool. powerful.
Yeah. Oh, and another thing I forgot to mention is that we're mostly interested in like local Hadwigers, but these algorithms, if you run it on like a single processor rather than in the distributed setting, they're very small polynomial runtime, which is also kind of nice.
Cool. If anyone has any questions, just feel free to unmute and you can ask. I feel like I want to ask something more about the distributed algorithms, but I'm not sure exactly what my question is. Or maybe just how did you get interested in it or get into it?
I mean,
I guess because you're working with Luke, but
yeah, Luke posed the problem to me and Ben, and I don't know, we really got into it. It was an interesting problem. I like local stuff. I mean, my master's was all really, really local, so I don't know, local is fun.
Neat. Well, maybe I'll end the recording there and then we can keep chatting. So thanks again, Lise.